be here. Thanks to all the organizers for inviting me. So now we're 3 talks into a conference about explicit class field theory, and I've noticed no one has mentioned the J function. Oh, that's really embarrassing. Somebody was late for your talk, Summit. Must have been right at the beginning.
Towards the beginning.
Okay, towards the beginning. Okay. Well, so let me be the second to talk about the J function. So, right, so we have modular curves, which we know parameterize elliptic curves, sometimes with some extra structure. And contained inside of those modular curves, you have CM points. And these CM points parameterize elliptic curves that have extra endomorphisms. So basic to this theory that over a field of characteristic 0, an elliptic curve has endomorphism ring, which is either Z or an order in an imaginary quadratic field. Okay, so endomorphisms by imaginary quadratic fields. Okay, so I call the collection of CM points. I might index these by an imaginary quadratic field K. So these are elliptic curves with endomorphisms by an order in K, which is an imaginary quadratic field. So in the arithmetic of modular curves and modular forms, well, let me say first that CM points on modular curves, I dare say they're the only systematic collection of algebraic points. So these are algebraic points. And if you look at this collection with complex of points that have complex multiplication by an order in K, these are algebraic points over some H over K, which is an abelian extension. And these are really the only, this is the only systematic collection of algebraic points that we know on modular curves. And in the arithmetic of modular curves, often where the rubber really meets the road is when you have some rationally defined mapping, and you apply that mapping to your collection of CM points, and you get algebraic results. So some examples of this, which may be familiar, so I'll talk about the top one in a second, would be explicit class field theory. So if you take the J function, the familiar J function, it's a function on the complex upper half plane modulo SL2C to the complex numbers, and it's given by, I'll write one term of the Q expansion. So it has this familiar Q expansion. Q is e to the 2 pi I tau. But what's really interesting is that this J function is actually a rationally defined algebraic function. The upper half plane modulo SL2C form the complex points of some kind of algebraic curve over Q, and it's a rationally defined function from Y to A1. Okay, so that's why if you apply the J function to a CM point, a point that has complex multiplication by K, the result is an algebraic number living inside of some abelian extension of the imaginary quadratic field K. And that's what gives you access to explicit class field theory in the case of imaginary quadratic fields. Okay, so explicit class field theory is one example. So another example would be sort of the theory of Heegner points. If you take the modularity mapping from x naught of n to an elliptic curve of conductor n that comes from the modularity theorem, and you apply that to these CM points, you get very interesting algebraic points on elliptic curves. Appropriate combinations of them are so-called Heegner points. And we also have things like if you, so this is the modularity mapping gives rise to Heegner points. If you apply this setup to modular units, meromorphic functions that only have poles at the cusps of modular curves, then you get very interesting so-called elliptic units. These generate interesting units in the unit group of the ring of integers of H. Okay, so this whole setup, it generalizes vastly from modular curves, so-called Shimura varieties. So let me just say a quick word about that. A quick, very informal word. Everything I'm going to say today will just be very high touch. So the classical case of modular curves, in that case, we have the complex upper half plane. When you mod out by a congruence arithmetic subgroup of SL2Q, SL2 over Q, so for example, SL2Z, you get the complex points of a Shimura variety, an algebraic variety over Q, in this case, an algebraic curve over Q. And if you take certain distinguished points in the upper half plane, those with imaginary quadratic coordinates, and you look at their classes, so they're special points, the ones parametrizing elliptic curves with complex multiplication, then this point lies in the H-valued points valued in an abelian extension of the imaginary quadratic field associated to tau, the so-called reflex field. And this setup generalizes vastly to certain other contexts where you have a special kind of symmetric space generalizing the upper half plane, so-called Hermitian symmetric domain, acted on by a much bigger group than SL2R, acted on by some big real Lie group, where G is defined over Q. And if you take a congruent subgroup gamma of the rational points of G, congruence arithmetic subgroup of G of Q, then the result is again the complex points of now a Shimura, we call it a Shimura variety. So this is again an algebraic variety over Q. And the same importance enjoyed by the special points, by the CM points in the case of modular curves, is enjoyed by so-called special points or CM points in the case of Shimura varieties. So this is a special point, tau. And if you take its class, it lives it's defined over an abelian extension of a certain field, the so-called reflex field that's associated to the point tau. So what is a special point in the context of a general Shimura variety? In general, so modular curves all parameterize elliptic curves with extra structure. The situation's not so simple for general Shimura varieties. Many of them, they parameterize families of abelian varieties, but not always. But sometimes, but always, there's a group theoretical perspective on what a CM point is. So a CM point, you can characterize it as a point which is fixed by the real points of a maximal torus T in the group SL2 over Q, which is rationally defined. Okay, so if you have a point that has imaginary quadratic coordinates, there's a certain torus inside the group SL2 over Q, whose real points fix that point tau. And that perspective generalizes to the context of Shimura varieties. So let me just write that down. So special points are points stabilized by the real points of maximal tori inside this group G. Special point. So these are points tau in this symmetric space, stabilized by the real points of T, where T is a rationally defined maximal torus. This setup is great. So there are certain maximal tori that special points on Shimura varieties say an awful lot about the arithmetic of, but it has one defect, which is that so a feature of these of non-positive curvature, so the negative curvature of these symmetric spaces, is that if you look at the stabilizer of a point in one of these symmetric spaces, it is a compact group. So T of R is compact because it's contained in the stabilizer of a point tau. So that means that at best, on a Shimura variety, all you could possibly see is the arithmetic of rationally defined maximal tori whose real points are compact, right? So in the case of SL2 over Q, you see the arithmetic of imaginary quadratic fields, okay, whose associated tori have compact real points, but you don't see the arithmetic of real quadratic fields in the same way. Okay, so that's a major motivating question for this talk. Not just of this talk, but of a whole program initiated by Henri. So we know that special points tau somehow see much about the arithmetic of maximal tori contained in this group G with T of R compact. But in this group G, there are always other kinds of maximal tori whose arithmetic you could contemplate. So the arithmetic of general maximal tori. whose real points are not necessarily compact. And we could ask, what should play the role of special points? Okay. So the simplest example of this, simplest instance would be, so if you take T to be the norm 1 units of a real quadratic field, K, contained inside the group SL2 over Q. So that gives a rationally defined maximal torus. Group of real points is isomorphic to R cross. It's a non-compact real Lie group. So what about these things? And is it possible that if we can cook up some Shimura variety-like object containing special point-like objects on it, that we could realize explicit class field theory for real quadratic fields? So is it possible that other number fields besides CM number fields fit into the sort of same paradigm as those kinds of number fields, that you should be able to realize explicit class field theory using meromorphic functions on some nice analytically defined variety, like a Shimura variety? Okay. So, whoops, let me use this board. So the brilliant insight of Henri is that there is a certain kind of symmetric space that does see that does have fixed points under the action of a rationally defined maximal torus defined over a real quadratic field. So so you consider the complex upper half plane cross a p-adic symmetric space, the Drinfeld p-adic upper half plane. Which is just P1 of CP minus P1 of QP. It's a short way of thinking about it. And if K if K is real quadratic and P is inert in K, then you take the norm 1 units of K. And you take the QP points of that group. It fixes points in the p-adic, the Drinfeld p-adic upper half plane. The real points of this torus, they don't fix any point on the complex upper half plane, as we were just saying. They do stabilize a geodesic, though, inside the complex upper half plane. So some geodesic going between these real numbers that have real quadratic arguments. So if you take the product of these things, you get some kind of one-dimensional object. The pair of this geodesic and this point is some kind of avatar for the real quadratic field sitting inside of H cross HP. Okay, so Henri's idea is that we should think of this H cross HP as being like a Hermitian symmetric domain, a kind of analytic space that uniformizes something like a Shimor variety. It's, of course, not a Shimura variety. We'll talk about this in a second. But let me call it a Shimura-like variety, given by H cross HP. And there is a group which acts naturally on this product. If you've thought a little bit about sort of locally symmetric spaces in arithmetic, you probably know that this group SL2Z1 over P acts in a nice way on the complex upper half plane across the Bruhat-Titz tree at P. And this HP is a kind of tubular neighborhood of the Bruhat-Titz tree. As a topological space, this kind of quotient is not that terrible. But what's really bizarre is thinking about this. We have any right to call this an algebraic variety or algebraic variety-like. We need to be able to talk about analytic functions on a space like this. Well, of course, those are just analytic functions on H cross HP, which are invariant under the action of SL2Z1 over P, you say. Okay, so we need to think about analytic functions on H cross HP. Then we get totally stuck. Okay, because H is an Archimedean object. There's a good theory of analytic functions on H, and there's a good theory of non-Archimedean analytic functions on HP. These are CP valued analytic functions. C and CP are totally incompatible with each other. Okay, so no one to my knowledge has thought of sort of a reasonable way that you can directly think about analytic functions on this space. So there's no direct way of thinking about analytic or meromorphic objects on a space like this. But the incredible insight that Henri had, and then sort of, so I'm not sure, Henri, if you're listening, when you sort of first started like mulling over these ideas. I know there's a paper trail going back to a paper that Henri wrote called Integration on H cross HP, where, oh, maybe I've erased the board already, but in that sort of diagram of things that we do to special points, it's like a theory of Heegner points and uniformization. But sort of going back to this paper, the idea was to like try in some meaningful way to make sense of this quotient, to make sense of analytic or meromorphic objects.
I'll point out that Henri had this idea in grad school.
Yeah, this was
So
paper trail goes
even
even okay, so
no pressure to any of the grad students.
okay,
Like that, yeah.
so going back to even I guess 10 years before that then.
yes.
Yeah, so the incredible idea is that, so I'm not going to write this down, but I'll say it out loud. If you there's an maybe I'll write something down. There's sort of there's an analogy between, if you take H cross HP modulo SL2 of Z1 over P, you should think of that as being analogous in many ways to a Hilbert modular surface. You take H cross H modulo SL2 OF, where F is a real quadratic field. And something you could do, so just to give you a sense that like, there's sometimes a way you can take an analytic object on a space like this and think of it in a more like component by component way and somehow disentangle the role of the two different components. So for example, if you take a holomorphic form of top degree on this surface, holomorphic 2 form, something you can do, holomorphic 2 form, you can produce from this, if you take that holomorphic 2 form, so what you can do is you can integrate out the first factor. So you have like this pair of complex upper half planes, let's just say parameterized by coordinates z and w, and you can integrate from z naught to w of z naught of this omega, a kind of partial integration. And when you do that, sort of the result is you get a cocycle for the group SL2OF valued in holomorphic 1 forms on the second copy of the upper half plane. So I'll call that HW. So this group SL2OF, it acts in a very non-discrete way on this copy, the second copy of the complex upper half plane. It acts discretely on a product of a pair of them, but it acts in a non-discrete way on this. And this kind of object that I've written down is like about the size of the thing that defines so-called rigid meromorphic cocycles, which we're going to think of as meromorphic functions on this quotient. Okay, so it's something that has this kind of shape, group acting densely on an analytic space, like in another coordinate, so to speak. And these kinds of groups, these cohomology groups, see shadows of analytic objects. In this case, this is a perfectly good analytic space. We can make perfect sense of what it means to talk about a holomorphic 2 form on this. Okay, and we see shadows of those things in these kinds of cohomology groups. So let me draw a diagram, just sort of like a cartoon picture of some of the things that we do in Shimura varieties and try to transport them, or say what has been transported, to these so-called Shimura-like varieties. Okay. So I think I want to talk about points, functions, and divisors. Okay, so these are Shimura varieties and Shimura-like varieties. Again, just to emphasize, like these things don't exist as genuine sort of algebraic objects, but if they did, what we're writing down would somehow represent shadows of those objects. So some examples of Shimura varieties, right? Our first example was upper half plane modulo SL2Z. Second example we mentioned was this Hilbert modular surface. Okay. So what are some things of interest on these Shimura varieties? We have points, sort of the only systematic algebraic points that we know on these Shimura varieties are special points. So these are points that have imaginary quadratic coordinates. I won't say it's slightly more complicated over here because the maximal tori in the group SL2 over F are a little bit more complicated than the group SL2 over Q. We have a good theory of divisors. So we can take H0 of gamma. So gamma will be SL2Z or SL2OF in these two examples, valued in divisors on this Hermitian symmetric domain, and the divisor has to be discrete. That's what I mean by the plus symbol. So discrete divisors. Discrete divisors which are invariant, of course, those descend to divisors on x infinity modulo gamma. And we have functions. So meromorphic functions, let's focus on. So we have h0 of gamma valued in non-zero meromorphic functions on this Hermitian symmetric domain. Those descend to non-zero meromorphic functions on x infinity modulo gamma. So we're about to move to a context where our sort of symmetric space, so to speak, modulo gamma, doesn't really make sense as an analytic space, but these definitions actually do carry over somewhat. So maybe the first hint is, what's the deal with special? So first, like I've mentioned one example of a Shimura-like variety.
Okay. I was gonna say in the divisors, there's like no topology left anymore, right? It's just a discrete. Right?
Yeah.
Somehow downstairs, there's still a topology left. Like the meromorphic functions.
Yeah. So you're just saying like I'm not I haven't said what divisor really means on.
Yeah, no,
I'm
I'm
not
just
talking about.
I'm saying like you could see that generalizing to other places where the topological picture is weird, like H cross HP. But somehow the bottom one still seems funny to talk about.
I don't see a way to talk. So I have to think about that. But I mean, I'll say later, like sort of what we mean by these divisors in the case of H cross HP and generalizations.
Okay,
But
yeah.
okay, so
I'll wait, yeah.
But these divisors are infinite sums, right?
these are infinite sums. That's right. And sort of they descend to some finite object on the quotient, which actually makes sense.
Oh, I see. Okay.
Yeah, that's right. So think of it as just like the pullback to sort of the whole symmetric space of an honest divisor.
Okay.
So you get this big infinite discrete sum. That's the plus, a discrete sum. Okay, so in the Shimura-like varieties. Okay, so this is the simplest example to emphasize just one more time. That doesn't really make sense as an analytic space, but we can make sense of these various things. So this picture that I drew of sort of like a geodesic sort of cross a point, which is fixed by a maximal torus, it actually gives rise to an object that lives inside of H1 of gamma p. So in this case, that's just our p arithmetic group, SL2Z1 over p, valued in 0 cycles on HP. Okay, that may seem to come out of nowhere, but it doesn't. Let me just explain for 1 minute why that definition, why that's a natural receptacle for the analogs of CM points in this Shimura-like context. So suppose you have one of these like T defined over Q associated, doesn't have to be associated to a real quadratic field. We just want T of QP to fix points in the Drinfeld upper half plane. So in order to have that, we just need the prime P to be inert in sort of the quadratic field, which is associated to T. Okay, so T of QP, so suppose that T of QP fixes, I'll say fixes O inside the p-adic upper half plane. There's a natural class in H1 of T of Z1 over P valued in Z. The assumption that P is inert in the associated quadratic field implies that this T of Z1 over P is actually an abelian group of rank 1. Okay, so this has a natural fundamental class. And there's a T of Z1 over P equivariant map from Z to 0 cycles on HP, induced by sort of the map from Z to 0 cycles, which maps 1 to O. Okay, so we map like N, and in Z, it's mapped to N times O inside of the 0 cycles on HP. And because O is fixed by T of QP, this mapping is T equivariant. So you really get a mapping like this. And then you can push it forward, right? This is a subgroup of our P arithmetic group, in this case, SL2Z1 over P. And so this thing maps, sorry for the sloppy board work, but this thing maps to H1 of gamma P 0 cycles in HP. So this algebraic object, it at least contains all of these things. We think of them as points, and they're indexed by quadratic fields that fix a point in the p-adic upper half plane, or in which P is inert. From the point of view of explicit class field theory, you might complain and say that, like, P isn't inert in every quadratic field, but of course, if you have a fixed quadratic field, there will be lots of primes that are inert in it. So you could sort of, depending on your sort of perspective on Hilbert's 12th problem, you could view this as being like a kind of approach. If you could make sense of defining a meromorphic function on that analytic-like space, and you could evaluate at these sort of analogs of points, then maybe this could possibly give an answer, something along the lines of explicit class field theory.
No, but I wouldn't think of this as evaluating a function on those points. Right.
So I think of a rigid meromorphic. So what is something which naturally pairs with this group? Okay.
That's what I'm saying. I guess like a code.
You take H1, that's right, of gamma P, and you take a meromorphic function on the p-adic upper half plane, there's a pairing between these invertible analytic functions and 0 cycles, and you get a number in CP cross. And so this naturally pairs with this. So if these are points, then these are functions.
Right, but I'm saying if you're taking an H1 and an H lower one and you're pairing them, that doesn't seem like evaluating a function at a point. It seems like integrating a function. Like it's just a this is philosophical mumbo jumbo, but like
I mean, like maybe this is also philosophical mumbo jumbo.
yeah, but like
because it's sort of like, I mean, what on earth does that mean as an analytic space? But yeah, so sort of the philosophy is think of objects here, sort of for right or wrong. Think of them as being sort of meromorphic functions on this analytic space that we can't actually define as an analytic space. And meromorphic functions have divisors, right? And so there's a natural gamma P equivariant map from a meromorphic function to its divisor. And so if we think of elements in here as being divisors, there's an extra condition. If you have a function, a meromorphic function here, and you take its divisor is discrete. Okay, so we think of objects of this group as sort of playing the role of divisors in this theory. So this column in this table was explored, has been, and is actively being explored in lots of depth by Henri and Jan. They thought very seriously about sort of all of the entries of this column. And the launching point for my project with Henri and Leonard was to try to think of like a more general context for like what are these or other families of examples of these Shimura-like varieties. Yeah.
So just for a sanity check, the three entries for special point supervisors and functions.
Yeah.
These don't seem like they're relying on H. Is that true?
Well, this is subtle. The dependence on H is in the one. Remember how I said that like the tori, like for associated to real quadratic fields, they stabilize a geodesic in the upper half plane. That one dimensionality is somehow like a shadow of the sort of the Archimedean part of the story.
That's what I was kind of getting at. It's like you're integrating out that Archimedean part by putting it in the one. So it's
Integrating out or taking some kind of intersection number. Yeah, it's true.
I mean, it's kind of philosophical to me. It's like you're integrating out that component of it.
So so we try to cook up sort of analogs of this whole column. I think the story may be more general than this, but we try to do this in the context. So like goal, complete this column. For general orthogonal groups over Q. Something you may know is that if you have, so an orthogonal group over Q has a real signature to it, and it's only the orthogonal groups of signature N2, which have an associated Shimura variety. But so we sort of wanted to fill in this column when the Shimura varieties don't exist. So sort of for general orthogonal groups over Q, not necessarily of signature N2, of general signature RS. And then sort of once you filled out this column, you can dream of many different things. If you've made sense of algebraic points, rationally defined divisors, and rationally defined meromorphic functions, you could go back to the first blackboard I wrote down, which is now erased, and you can start to dream. You can start to say what happens when I take a rationally defined meromorphic function and I evaluate it at an algebraic point defined over some prescribed abelian extension of a kind of reflex field. What would you expect to get? So you'd expect, maybe less than half the battle, not maybe less, definitely less, but a part of the battle is even making sense of sort of what should go down this column for general orthogonal groups over Q. So we cook up another Shimura-like variety. The role of SL2Z1 over P now is played by, if you have a quadratic space over Q with a lattice inside it, you can make sense of the integral points of that orthogonal group or the P integral points of that orthogonal group. Okay, so this is like SO, I'll just abbreviate it gamma P. So this is like the P integer orthogonal group.
What do you mean by P integer, meaning inverting?
There's the 1 over P points of the associated orthogonal group. And for a general quadratic space of signature RS, you define sort of analogs of points in a very analogous way. So we define classes inside here, defined on with values in 0 cycles on XP. And these are associated to rationally defined maximal tori in these orthogonal groups, which are as split over R as they can possibly be. Okay, so like the analog of the norm 1 units of real quadratic fields, those are tori which over R are as split as possible in SL2 over Q. We want to pair these classes. They pair naturally with classes in here. So we'd love to be able to construct elements of a group like this. And the way that we're going to access these meromorphic functions is they're a little bit hard to get your hands on. What we'll try to do instead is we'll access the divisors and then try to develop a theory of when those divisors actually are principal, when they lift to functions. Okay, so we're going to study these divisors.
Is S the dimension of X infinity?
So S is like this, it's this, so dimension of X infinity is R times S. So S is like, it comes from, you have two integers R greater than or equal to S. That's the signature of your quadratic space. So that's the same S.
Yeah, okay, and the dimension of X infinity is R times S. Interesting, okay.
Yeah. And if you look at the Z 1 over P points of the tori that fix points in the XP that I haven't defined yet, they're essentially free abelian groups of rank S. That's the significance of S. So here,
Sorry, yeah. Sorry.
so we wanted to understand what Henri and Jan were really doing in the case of there's an accidental isomorphism between PGL2 and an orthogonal group of signature 2,1. And so we wanted to understand better in this other context what they were doing, how what they were doing would generalize to this new column. We wanted to put it in this slightly bigger context. So all sorts of things that I've written down so far are undefined. Let me give a little flavor for what different things are. So we start with a quadratic space of signature RS over Q.
I'm sorry, can I interrupt just briefly? The signature here, R is the positive definite part, S is the negative definite part? Is that?
Yeah.
How come R has to be bigger than or equal to S?
Well, in the one of these two numbers is bigger than or equal to the
Okay, so
other.
you're saying
Just
it's- the theory will be symmetric is what you're saying.
Yeah. That's right. I mean, you could take your quadratic form and you could take its negative, and then that would reverse the R and the S, but the orthogonal group doesn't change. So, okay, so given this this data, we want to a p-adic symmetric space XP. We want to a usual symmetric space X infinity. The second thing is old news. That's well known. It's well understood what this X infinity is. I can say right away, this is just, you can think of this as the set of negative S dimensional planes in VR. Okay. And then once we have this, we want to like construct rationally defined divisors. And hopefully, if these divisors are natural enough, have a theory of principal divisors. So when linear combinations of these various divisors are actually principal. So when do they lift from this entry of the table to this entry? Thus giving you a hope of actually, defining a value of the corresponding function at a given special point. So you want to construct rationally defined divisors and functions. The divisor part is not so bad, and I can explain. The function part is much deeper. And then we want to evaluate. So these functions are sort of like, I'll call them J in homage to the J function. And then, so these special points So we want to evaluate j of tau, where this is a special point. Associated to a maximal torus defined over Q, which fixes a point inside of this p-adic symmetric space that I owe you a definition of. Okay, so when should I stop? At 5 minutes? 10 minutes?
Up until.
10 minutes.
10 minutes? Okay. Um, Cardinal sin is going over, especially when everyone is hungry to eat lunch. This is like a very dangerous speaking slot. I'll just have to exercise some constraint, right? Restraint, excuse me. So, so I've said what this x infinity is. Okay, so Q, this is a quadric of isotropic lines in V over CP. And we define XP to be this quote, and this, by the way, this is a, I mean, this is like some flag variety for the orthogonal group, for the corresponding orthogonal group. And if we take that quadric and we delete those lines L, the orthogonal complements of those lines L, which are actually defined over QP. That's the definition that we give of our p-adic symmetric space. So that's contained in this quadric of isotropic lines. I only have time to say so much. Something that is not so well known, or certainly was not known to me before I started thinking about this more. In the case of signature N2, you can actually give a totally analogous definition for the real symmetric space, where you just sort of replace L over QP by L over R. Okay, so this definition doesn't come out of nowhere. It's very analogous to sort of the Archimedean definition, just like P1 of CP minus P1 of QP is very analogous to P1 of C minus P1 of R. So we can define certain Archimedean cycles if you have a real vector in your quadratic space. So you can look at the set of planes, so negative S planes that are perpendicular to a given vector V, okay? And that's a sub-symmetric space associated to an orthogonal group of signature R minus 1 S, in the case where V is a positive vector. You can write down a totally analogous definition of a, in this case, it'll be a divisor on the associated p-adic symmetric space. You look at the set of these isotropic lines, which are perpendicular to the vector V. That's if you have a vector V inside of QP. I don't know if our terminology on this is great, but we call these, I actually don't know if we call these, or the sums of them that I'm about to define, we call them Kudla-Milson cycles. Because they're very analogous to certain cycles that Kudla and Milson defined in a early Archimedean context. So we define so a certain so fix a positive integer d, and we can define Okay, let me actually just do this in the case of signature R1, because I think everyone will buy what I mean here a little more easily than in general signature. So if you take this P arithmetic orthogonal group, we can define a homogeneous cocycle in the following way. So you map the pair gamma 0, gamma 1 of elements in this P integer orthogonal group. You map it to the following divisor. You take the sum over all. I should have said, I don't remember if I did, fix a lattice L inside of your rational quadratic space. So you sum over all of the P integer vectors. Sorry, was there a question? That have norm equal to D. And you take the so Samit, this is your integrating out. You define the, so you intersect this Archimedean cycle with gamma 0. So fix a base point O inside of the real symmetric space. And you take the intersection number, the signed intersection number of this thing that I've written down, which is the geodesic connecting these 2 points in the real symmetric space. And you intersect it with this. So in this case, in the case of signature R1, it's a codimension 1 cycle. So the intersection is just this intersection number is some integer. And you multiply that by delta VP. Okay. And you can check that this actually defines a discrete divisor inside of XP. You have to take some care about the choice of base point because it's only when this geodesic is transverse to all of these delta V infinities, of which there are infinitely many, that these intersection numbers all make sense. That's quite easy to do in the case of signature R1. It's harder to deal with in the case of signature RS, but that's a technicality we're able to sidestep in our paper. And this has good formal properties. So it is a homogeneous in a totally formal way. And also in a very formal way, just because of how the intersection of a compact chain works when you intersect compact chains with sort of so-called Borel-Moore chains of the complementary dimension, it's kind of this is also quite formal. To say that if you evaluate this thing on a chain, which is a boundary, you get 0. So in other words, this thing actually defines a 1 cocycle for the P arithmetic group. Okay, so let me just, I'll just end with, I'll state a theorem. That's basically all I have time left to do, then we'll stop. Okay, so the theorem is that the construction generalizes to give these divisors in this cohomology group. Okay, I'll just say that we conjecture, I'll call it a Borchard's theory of principal divisors. In other words, we have a very good guess of when integer combinations of these Z sub D should correspond to principal divisors, and it's governed by sort of a linear. Let me just say, sort of linear combinations of Fourier coefficients, those functionals basically of level gamma naught of P times this is imprecise, but I'm just going to say it like this. So if you know sort of about Borchards' theory and sort of the case of orthogonal groups of signature N2, maybe you know what I mean sort of exactly by this. Otherwise, if you ask me, I can explain. We have a theory of which linear combinations of these things are principal. We prove this in special cases. So we prove this in signatures R0 for all R. Sort of 2-1. So that's sort of the work of Henri and Jan. And also signature 3-1. And let me just cram in one more thing. So we make conjectures about algebraicity of singular moduli, which when you check on a computer, they actually seem to work.
Have any data to show us?
I do. Okay, so make conjectures about algebraicity, which seem to work, at least in signature, sort of this brave new world of signature 3-1. And I'll just say that the key input is Kudla-Milson theory. And technicalities related to Kudla-Milson theory are the reason that we sort of can't prove a statement like this more generally for totally general signatures, at least yet. Although there is we have some ideas about sort of different approaches to possibly lift the right linear combinations to meromorphic functions that are sort of totally different and will also be much harder to compute with. But let me stop here. Sorry for going over time.